Alright, in this video we're going to go through some of the technical aspects that surround IPv6, a little bit about the history of why we're using it, and how it's changed since IPv4. So it's more than just looking at hexadecimal 128-bit addresses. There's a lot of really good features in IPv6 that we need to know about, and how the routing process behind that has changed as well. So what we're going to focus on for at least this video is just that background information, the technical details of it, and then we'll get into some configuration examples here in different videos as well. So IPv6, why are we using it? Obviously the big thing that comes to mind for many of us is the address space limitations in IPv4. So by now you've probably heard we're basically out of IPv4 addresses. You can still buy them, but you can't just get them as directly as you used to be able to. And so with IPv4 being a 32-bit address, there was 4.3 billion addresses or so. And think about how many people actually exist in the world today. The last I checked, we're at about 7.4 billion people, which is almost double the amount of IP addresses that we have. Now the interesting part about that is, of those 7.4 billion people, there's really only about 10% of them online. So as you know, that large businesses and even universities and home users may have more than one IPv4 address, depending on what they paid for and what that setup looks like. So some of the things that are different in IPv6 that we had in IPv4 and really relied on were things like CIDR, NAT, and variable length subnet masks. So NAT, of course, remember the big thing that was PAT, or port to address translation, allowing us to have many devices behind a single IP address. So that's really common in the networks that we see today, is people using different variations of NAT. And again, variable length subnet masks allowed us to have different sized subnets within a network. So rather than having a slant 24 between our two routers, it allowed us to have a slant 30 between routers, and maybe let's say like a slant 26 for a different host subnet. So it was allowing us to have different size networks and really to break up those blocks more efficiently. IPv4 has been around for a long time, and actually IPv6 has been around for quite some time as well. But with IPv4's age and its adoption rate, many of the features that you see within there have been added on. And IPv6 looked at those things and took a lot of the good features and then just baked them straight into the protocol. One thing I think about this is IPsec. So we oftentimes think of IPsec as being used for just like VPNs or other secure communications, and that was an add-on in IPv4. By default in IPv6, IPsec is enabled for all of our communication. So we're getting a little bit more secure stuff with IPv6. So as you can hopefully kind of start to see, this is more than just more addresses available. It's also more secure, and it's going to be a lot more efficient here as well. And then we know devices coming online is growing exponentially. Think about it's kind of an interesting exercise. Just look at the room you're in and count up the devices that you have all grabbing an IP address. Think about it, things like our tablets, our phones, laptops, even TVs, Xbox, whatever else you might have going. A lot of those devices are consuming IP addresses. So we think about some of this stuff and furthers the need for adopting IPv6. So I pulled this graphic off of Google, and they had a little brief write-up about IPv6 and where our numbers are at. But this basically sums up what I was just talking about here. You can see that red line there, IPv4's limit, is just under 4.3 billion is what we said. According to Google, our actual internet users has crossed over that 5 billion mark. So we have more internet users than we do IPv4 addresses. But look what's happening with the connected devices. Now, of course, these aren't all connected devices that are publicly facing. These are devices maybe sitting in our internal networks, but are still accessing the internet somehow. So this could be over NAT or different configurations like that, more than likely. So what do we get with IPv6? We talked about a few of these things already. So being that it's a 128-bit address versus a 32-bit address like we saw in IPv4, we've got 3.4 times 10 to the 38th addresses available. So really a massive number of public IP addresses that we could use with IPv6. Now, one of the interesting things a lot of people kind of say about IPv6 is the amount of addresses that we have available. We could apply one address to every grain of sand on the planet and still have enough. Now, hopefully from your reading and some of the research you've done, that's not entirely accurate, because ISPs and different registries are taking up to 64 bits of those available 128 bits and giving those per network. So it's not a specific one-to-one thing, but it's still an interesting number to look at. We talked about IPsec being built in, and IPv6 is more efficient than IPv4. What you'll notice with IPv6 is that the packets have half of the fields as they did in IPv4. And the other thing that's really beneficial about that is they're aligned on a 64-bit segment. So if you think about that, if all of our fields are aligned at 64 bits, it makes our processing and the calculation a lot easier. Because if I know the next field is always 64 bits away, I don't have to search the packet, find the offsets, calculate all of that stuff. I just keep looking at 64-bit increments. So a lot of the headers were stripped out of IPv4 that were now optional, so we only are using the headers that we really specifically need. That just makes our packets a little bit smaller, a little bit more efficient here as well. IPv6 has better multicast support, and a lot of the routing protocols and things you'll see in IPv6 do depend heavily on multicast. And one of the really big things I think is a huge benefit of IPv6 is that we've done away with broadcast traffic entirely. So just kind of a recap from previous routing and switching courses, we know that we had problems with broadcast traffic, especially in a switched environment. So if we had switching loops, we could get broadcast storms, which would effectively bring your network to a halt. Also, broadcasts just interrupt every single device that's in that current broadcast domain. So by not having to deal with that, our network should just run a little bit smoother, cutting down on some of that traffic that doesn't need to be seen by everybody. So to give you some sort of an idea of what this looks like, and we'll look a little bit more in depth at this too. Your IPv4 packet headers were pretty big. We saw a lot of different stuff in them. And your IPv6 packet headers has a lot of those same fields, so your IP version number. We'll look at, I've actually got a graphic here with the exact fields highlighted of what stayed the same and what's different now. So we'll come back to that. But in IPv4, our headers were 20 bytes long. IPv6, we're looking at a 40-byte long header. And this is interesting because we think of IPv6 being effectively 4 times bigger than IPv4. So a lot of people would assume that the headers would be 80 bytes rather than 40. But like I said, they trimmed out some of the extra stuff out of IPv4, gave us specifically what we need. And so the headers are twice as big, but again, it's still going to be more efficient. Long story short, just these packets are crafted much better. So here's what we're looking at with all of the things that are really kept over the same from IPv4 to IPv6. So we had stuff like our IP version numbers, the traffic class or type of service, those two are the same things, source and destination, and there's really not a whole lot extra sitting in IPv6. So hopefully you can see that, even though it is 40-bit or 40 bytes, this is going to have a lot more stripped out versions of what we saw in IPv4. So the big important ones in IPv6 that we saw also in IPv4, so your version, traffic class is like your type of service, so it's just a renamed field in there. Your flow label, so it just keeps track of your packets from a sequence from each host they touch or what they're going through. The length of it, so IPv4 used the actual length of the total packet. IPv6 just calculates the length of the payload. So remember, if these fields in the packet are all calculated off 64-bit offsets, the only really varying thing in IPv6 that might be different from one packet to the next or one transmission to the next will be that actual payload size. And a good example is this, think about if you're using something like TFTP, very small packets going across, compared to like a large HTTPS stream or something like that. The payloads in those packets are most likely going to be different sizes here. Next header, just for using any different headers. So remember, IPv6 uses optional headers, where IPv4, every packet had the same headers whether they were used or not. Your hop limit, how many destinations or how many routers can you go through before the packet needs to just expire and not be transmitted. And then source and destination addresses should be pretty self-explanatory. So we've talked about IPv6 a little bit. We haven't actually looked at one of the addresses here. And one of the first things people usually say when I ask about what do you think of 6, they say the addresses are huge, they're long, and kind of difficult to remember. But we'll look at this and kind of break it down on how to make IPv6 a little bit more manageable and easy to remember when we're typing stuff in. There's no getting around it. Being a 128-bit address, it's just going to be quite a bit longer. So you can see here we have 8 groups of hex digits, and they're all separated by colons. You can compare that to IPv4. We had the 4 octets separated by periods. Really same purpose, just a little bit different way of expressing that. So if you think about what hex is made of, 4 hex digits is equivalent to 16 bits. So if we take that, we should have 16 times 8 would give us the 128 bits. So there's going to be 8 blocks of 4 hex digits in all of that. And you can see here, like I said before, when we're talking about the, there's enough IPv6 numbers for every grain of sand. That's, true, but it's not actually what we're going to get, and it's not what's actually practical. So what you're actually going to notice is the biggest IPv6 block you're ever going to get from an ISP will be 64 bits. And the reason for that is your registries, your ISPs, break things down into company names, and all of that stuff adds up to about 64 bits. So that's that first part here in yellow. What you actually get to assign as your host IDs is going to be the remaining 64 bits, which is still really, really huge compared to, what we saw with IPv4. I put this URL down here just for a quick example. It's not often that we're going to have to type in a IPv6 address into your web browser, but if you do, obviously the colon is reserved for things like ports in typical browsers. So if we're actually going to navigate out to an IPv6 address in a web browser, you just have to enclose that address in square brackets, and then it should go. So you can try this out if you do have IPv6 enabled on your network. You should be able to find the IPv6 versions of like Google and Facebook, and Netflix used to support it, but I believe they've since redacted that out of their support for now. In any case, we can see with that, DNS is going to be a hugely important thing with IPv6 coming up. So if you do have IPv6 support enabled, whether it's from your ISP or your company or whatever network you're plugged into, you can subscribe to things like Google's IPv6 DNS and start to browse the web, over IPv6. So with these big ugly addresses that we have to remember, you are going to have a good understanding as like a network administrator of setting up IPv6 in DNS and using that, relying upon it. But there's times where we don't need a DNS address on everything, and when those cases arise, we can actually abbreviate IPv6 addresses, which is really nice. So if we started out with an address like this 2001 0D B8 3C 4D 0012 and so forth, that's a fully typed out IPv6 address. So all 128 bits of that address are represented in the hex values. So if we've got our 16-bit blocks, there's 8 of those blocks, that's the entire address. Now there's 2 things you can do to shorten up a IPv6 address, and it doesn't affect the functionality at all. This is just for us as we're reading these out, as we're typing them, trying to remember these addresses. Here's what we can do. Any block that you see that has a 0 as the first digit, or a consecutive set of zeros, we can remove those. So if you take the address that we originally started with, just go through each block. You can see the second block here had 1 0, so we'll just get rid of it. The fourth block had 2 zeros. If we have consecutive zeros within a block, and it leads off with a 0 followed by more zeros, we can get rid of those. So what I'm doing for right now is removing all of those, but leaving at least 1 digit in every single block. So remove 1 from the second block, remove 2 from the fourth block, 3 from the fifth, 3 from the sixth. So I'm leaving some zeros in here as well. And what you get is an address that looks like this. So you can see it's considerably shorter, but there's still more that we can do to shorten this up. If you have a block with only zeros, we can replace one set of these blocks with a set of double colons. So look at the address we had from the last slide. So this was our originally shortened one. We had a couple of blocks that only had a 0 in them. So what I'll do is I'll find those, combine them together, and just represent them with a set of double colons. So what these double colons means is that we just had at least 2 or more double, blocks with all zeros within them. We'll look at some more examples that'll kind of make this a little bit more clear. But this is a topic I would highly recommend that you practice and get familiar with. It's good for quiz and exam type things. If you're going to take certifications like your CCNA, this kind of stuff is in there as well. Now, from a practical real-world stance, there are websites that'll help you shorten this, but it's really not difficult to do, and it probably actually is faster just to do it in your head or quickly write it out. So it's something I'd encourage you to practice with, and I'll give a couple more examples here as well. Now, there's one problem that we have with replacing those contiguous blocks of zeros. And the rule is, if we have contiguous blocks of all zeros, we can only replace one of those with double colons like we did in the last slide. Now think about this, it kind of makes sense here a little bit. If I look at this address, I see that I have 4 blocks that are all zeros. And since I've got some contiguous blocks here, we could replace those with with a double set of colons. So my address could become 2001 : 0012 and so forth. Or I could replace this set of zeros with double colons, but you can't do both. So I can't do double colons here, can't do double colons here. If you think about it, there's just not enough information in that address to tell us where all of those zeros go. So should I have 3 blocks of zeros here and 1 block of zeros here? Is it 1 block here, 3 blocks here? Is it 2 and 2? There's just not enough information for us to actually figure that out. So that's the reason that we can only replace 1 block of all zeros. And the default that you do for IPv6 is we find the largest contiguous block of zeros and replace those. Since these were equal, I had 2 and 2, we just replaced the first one. If I had all zeros here and 3 blocks here, we would replace the 3 together. So you replace the largest set of all zeros that you can see. So let's take a practice example here. And this is something maybe you want to pause the video, or you can watch this one and practice with it, but kind of figure out what you would summarize this as or how you would shorten it. I'll go through it here. So we have this big long address, and the first thing we're going to do, just like we did before, we're going to remove all leading zeros. But if our block has all zeros, we're going to leave at least 1 0 in that block, just so we can keep track of where those were. So here's what we end up with. Removing all of those leading zeros, I get 2001, DB8, 0B, 000, 1A. Now, like what we did before, is we find our largest contiguous block of all zeros and replace those using a double colon. So what we can see here is that I have a single 0 there, and I have 3 blocks of zeros here. So obviously, we're going to compress these 3 blocks of zeros and represent them as double colons. So what we get is the address of 2001 DB8. We had to leave this 0 because there wasn't enough information in the IP address to get rid of that one. B are double colons, and this is where those 3 blocks of zeros were, 1A. So it's pretty interesting. If you look at this big long address that we started out with, just with 2 simple steps, we can get something down to this. Again, it's not as friendly as IPv4, but it's a lot easier to read than what we started with, and it saves you typing as well. I've got one more example here for you of compressing the IPv6 addresses. So again, we're going to go through the same process. First things first, remove all of the leading zeros from the address, but leave at least 1 0 if your block contained all zeros. So we get 2001 DB8, A0B, 12F0, 001. Next step, compress the largest set of contiguous zeros using the double colon. Well, in this case, it's pretty simple to look at. We actually only had 3 blocks of all zeros, and they happen to be contiguous, so we're going to compress that address right there, and we come out with 2001 DB8 A0B 12F0 : 1. So again, take some time to practice that, get familiar with it. As you do more IPv6 work, this will come a little bit more naturally to you, but it's just 2 simple steps, and if you have to write it out, that's fine. But eventually I think you'll be able to sort of just memorize this or do it all in your head as you're working as well. So let's talk about address types a little bit here with IPv6. So a couple things to remember. Broadcast traffic is completely gone from IPv6, so we shouldn't see any broadcasts happening there. IPv6 still uses unicast, and that's the exact same thing like we saw in IPv4. So it's just, one packet going to a single address. So one-to-one communications with unicast. We have global unicast addresses, and these are going to be things that are publicly routable addresses. So in IPv4, if you think about the internally non-publicly routable addresses like 192.168, 1. Whatever, we have those in IPv6 as well. But these global unicast addresses will be the ones that actually are publicly routable. So like what I talked about before, your ISP gives you basically 64 bits to assign to your host address when you actually look at that map and see what's taken up. And here's a good graphic that actually explains how that's happening. So you can see that your registry takes up the first 23 bits of the address, and that's something like RN or one of those registries. Your ISP gets the next 9 bits, so Midco, SDN, VAST, whatever your ISP might be. They can assign up to the next 48 bits. That would be, so they get 16 bits to assign to companies. Within that, you get the 16 bits for different subnets. And then lastly, you have 64 bits for your actual interface IDs. So your addresses do get taken up a little bit, and that kind of comes back to when we talked about a couple times now, how people say that there's enough IPv6 addresses for every grain of sand. Well, it's not really true because a lot of this address space is actually reserved. And it's just the way it works, but we still have a ton available. A couple more important address types that you're going to need to know about. Things like link local addresses, and this is like your APIPA addresses we saw with IPv4. And APIPA, remember, is if you plug into like a switch or something, your computer's set for DHCP, can't find a server, you get assigned a 169 address. Now, all of those 169 addresses can talk to each other, but they can't talk to anything that's routable. So we see the same thing. It's called a linked local address, and it starts with FE80 will be your prefix for that. So anytime you see FE80, we just think of that as like the 169 equivalent of what we saw in IPv4. Your unique local address is FC00, basically our internal address scheme that we have there. So this would be like your 192s, 168s, your 172s, whatever network scheme you're using. That's going to be like the internal equivalent of that. Multicast addresses are used for a lot of different things. So some of our routing protocols, discovering other routers, so figuring out who our neighbors are, that type of thing, always starts out with FF. And then probably my favorite thing that they've done with IPv6, and I think it's very interesting, is Anycast. What Anycast allows you to do at a high level is assign the same exact IP address to multiple hosts. And what this allows you to do is when you're communicating on a network, your router is going to find the nearest host with that address, and you're going to communicate with that host. So think about this. If we had a replicated file share in 2 remote sites. So I had a file share sitting in Madison and maybe a file share sitting in Sioux Falls. And those 2 file shares just replicated, so exchange the information back and forth automatically. Well, if I'm in Madison, I can type in the IP address to that file share, assuming we're using Anycast, and it's going to direct me to the Madison file share, right? It's going to find the closest one that has the address I'm trying to get to. Users in Sioux Falls, same thing. They'll type in the exact same IPv6 address as I did, but the Sioux Falls routers are going to know, hey, this host is actually closest here, so we're going to have to communicate with that. What that allows us to do is communicate with the closest hosts, more efficient, saving bandwidth. We're not relying on our WAN links. It's a really cool thing, and we're going to look at setting up some of that stuff a little bit later on. So I'll go through this in a different video here, but just to give you the commands of setting up IPv6 in the network, we've got that there. One of the other topics that we talk about is auto configuration with IPv6. So rather than us coming up with a unique IPv6 address for every host, and it's not that difficult to do, what we can do is give our hosts a prefix, so basically tell them what subnet they need to belong to, and let them make up their own unique address. So the way this works is hosts will actually look at their MAC address, which by now a MAC address is 48 bits. They'll pad that MAC address with the hex digits FFFE, and that makes it 64 bits total. And they'll add that on to the 64-bit prefix that you gave them. So what this allows you to do is just kind of like auto-configure your hosts and let them make up their own IPv6 addresses. Saves you a little bit of typing out if you don't really care what your hosts are getting addressed as, but it's something that's pretty useful for us. So let's just go through this example here. If we take this MAC address here, 0060D673 1987, what we do is we count in 6 hex digits. So we count in 1, 2, 3, 4, 5, 6, add in FF:FE, so right in the middle of that. Then we should have 6 hex digits remaining, and that makes that a 64-bit address. Now, the way this works is we also have to specify, is this address going to be locally unique, so more of an internal address, or is it going to be globally unique, something we could actually have routed on the public internet? So what we do is we take the 7th bit of this, and I've got some examples of this. We take the 7th bit of that address, and we flip it. So we have to convert it to binary, flip that 7th bit, and this will help designate, is this a link local, or a locally unique, or is it a universally unique address? So take this for example. I took my 48-bit MAC address, I padded it in the middle with 16 bits. I take the first 2 hex digits and convert them to binary. So it's easiest if you go hex to decimal, and decimal to binary if you're doing it manually, or if you just have a hex calculator, just switch it from hex to binary. So what we do, we take this, count out to the 7th bit, and if it's a 1, it'll be universally unique, so meaning we can route it out on the public internet. If it's 0, it's going to be locally unique. So let's start out with an example. If I use the prefix, so this is like my subnet, of 2001 0DB8 0000 0001, and the MAC address of 00902716 FD0F. So remember, the first step that we need to do is we're going to count in 6 digits, and this all happens automatically, but it's important to know how this process works and be able to do it by hand just to understand it. But again, your routers will do this automatically. But in any case, I count in 6 digits, so let's just grab a pen here. So I'll count in 1, 2, 3, 4, 5, 6. That's where I'm going to insert my FFFE, and then I'll have the remaining 6 digits following that. So what we get is 009027FFFE16FD0F. Okay, and that's a 64-bit address again. Now what I need to do is modify my 7th bit and flip it, and that's going to tell me if this is going to be locally unique or globally unique as well. So 00 is the first 8 bits of my MAC address. So 00, if we converted that to binary, will just be all zeros, so that one's pretty simple. Find the 7th bit, which is right here, and we're just going to flip it. So it comes 00000010, which is 2 in binary, and so our 64 bits that we have becomes 029027FFFE16FD0F. If we add our prefix to that, this will become our automatically assigned address. Now it sounds like kind of a complicated process, I know, the first time we look through it, but a couple important things I really want you to focus on and remember. Again, the reason that we do this is it saves us some typing, saves us thinking about our addressing scheme a little bit. We just let the router handle it. The router does all of this calculation, all of this math for you, padding the MAC address, everything automatically, so you really don't have to worry about it. For an exam perspective, a certification perspective, you need to know how to do this by hand, but practically, it's not something you really need to touch too often. So let's do another example here. We start out with this MAC address and our prefix like we did before. We're going to just go through the same things here a little bit quicker, and I'll give you one more after this to take a look at. So again, first count in 6 bytes. So 1, 2, 3, 4, 5, 6. We pad the MAC address with FFFE. We get the remaining 6 hex digits out there. Step number 2, convert the first 8 bits of hex into binary. So our first 8 bits were AA, which if you want to think about it this way is 170 in decimal. Comes out to 10, 10, 10, 10 in binary. Find the 7th bit and flip it. So we went from a 1 to a 0, and that gives us A8. So we just add in our prefix, which was all the way up through here. You can see our A8 where we flipped it, part of our MAC address, the padding, and the last part of our MAC address. So if we just let the router take care of that, we're going to have a really quickly assigned, unique, simple address for that interface. Take one more example, and I'd encourage you to go through this a little bit, so maybe pause it and think about this one a little bit. But we're going to use the same prefix as we did in the last slides, so if you want to write this down, prefix was 2001, 0DB8, 4 zeros, and 0001. So we're going to use that prefix. We're going to start out with this MAC address. So again, your first step, you're going to pad it with FFFE. You're going to convert those first digits of the MAC address, so your 0B, convert those into decimal, or go straight from hex to binary. Flip your 7th bit and add in a prefix for that. So let you work through that one on your own here. So there's another thing we can do here, and that's letting the router do some auto configuration for us in a network. So this is more for like host-oriented thing. So if a host needs prefix information, so a host is going to automatically assign itself an address, maybe using EUI64 like we did before. And all it really needs is that prefix information, so it doesn't really know what subnet it needs to be on. It's going to query that from the router. So step number 1, host needs that prefix information, and this was like basically the network portion of an IPv4 address. It sends out a router solicitation request, and that's sent to FF02. Remember what we talked about before, anything that starts with FF is multicast, and it's actually going to put this in a ICMP message. So it sends out a router solicitation saying, hey, I need a prefix for my network. The router is going to respond back to that via multicast, and you can see the ICMP type field gets changed from 133, the solicitation, to 134, which is your router advertisement. And it's going to send back to host A and just say, hey, this is your prefix that you need to start working with. So host A knows what network it needs to be on. Then it can go through that EUI64 process and assign itself an address. So that's maybe a little bit better example of why we would be using that stuff. So this is called stateless auto configuration, and the reason is we don't really contact or connect to and receive information from any other device like a DHCP server, anything like that. We just ask the router, hey, what prefix are you using? I'm plugged into this port here. Router sent it back to us, and we just kind of came up with an address on our own here. So another good example of auto configuration here is if we look at this one where I've got a branch and a corporate router, and they are connected to the internet through that corporate router. So if the branch needs an address on gig 0, so it's trying to talk to the corporate router and hopefully get out to the internet using IPv6, we can use some different auto configurations for it. So I'd use this example if I don't like typing in a IPv6 manually on that interface. I would use this if I don't want to do any routing manually, and I need more than the link local address, so it's got to be like a unique address here. There's a way we can do it, and it's just a simple command, and we'll look at this too in a practical example, but basically all you do is you type out IPv6 address, autoconfig default. What this does is pretty much the same thing as what we saw in the last example here. The interface will send out a router solicitation. The corp router should send back a route advertisement with the prefix. And so gig 0 on branch is listening for that router advertisement to come back. And then it'll use EUI64 and assign itself a global address. Okay, so it used EUI64 to make up its own address that's on the same network as gig01 from Corp. So again, I didn't have to really configure anything. I don't necessarily care what that gig0 address is on branch. I just wanted it to be configured, talking to Corp, and get out to the internet. Now you notice at the end of that command there in green, this is the word default. What that does is it'll grab the default route from Corp. So the default route from Corp should be pointed to the internet, and it'll inject it into the branches routing table. So really cool stuff there. I didn't have to make up an address. I didn't have to do any routing. I just said, hey, go out, get an IPv6 address, get the default route to the internet, and then walked away from it, and it configured itself. So it's harder to see these benefits unless we actually get into stuff, and we will. But just keep in mind IPv6 is helping us do a lot of this work we have to think about manually, and it's really automating that in a really efficient way for that. So that was stateless auto configuration. IPv6 also does stateful auto configuration, and this is what we'd call DHCP v6. So really, same thing as version 4. Still provides mention of your DNS and domain names. Your auto configuration is just address based. And rather than the traditional DHCP request, DHCP reply that we would get in an IPv4 network, our hosts that need an address from DHCP fall back to those router solicitations, the RS, and router advertisements. So again, just keep that fresh in your mind. That's happening over multicast, and it happens with ICMP packets that have the type field sent to 133 for the router solicitation and 134 for the router advertisement. So what happens basically is the host sends out that router solicitation. It tries to find a router. If a router is not found, the client will send out a DHCP solicit. So it's a different type of multicast packet. So hopefully a DHCP server listening on the network will see that and respond back to it, help configure our host for it. Now it's interesting, Cisco doesn't really support DHCP6 very well. So we could do DHCP, in version IPv4 on a router, and it was pretty good. Most companies, most networks still use a separate server for DHCP. And that's basically what the case is with DHCP v6. You can do a little bit of it directly on the router and use your router as that DHCP server, but still the recommendation is set up a standalone, separate DHCP box to do v6. Basically what the router will let you do is it'll let you assign like DNS, domain names, default gateways, and SIP servers, but it really doesn't do anything well for you, or even to give you the option to do address management of the pool or some of those other options you might set with DHCP. So we're going to kind of stay away from that a little bit. And while we're talking about different protocols like DHCP in this IPv6 world, one of the big important ones is ICMP. So you've already seen that ICMP is used for things like your router solicitations and advertisements, but IPv6 uses it for quite a lot of different stuff. So it's not really a separate protocol anymore, it's just used as an extension header. It's one of those optional add-on headers to that IPv6 packet. Some really cool things about this is it prevents fragmentation by discovering the MTU packets. And we'll talk about this here in a second. MTU is basically the size of the packets that you can send. 1500 was a default MTU in IPv4, if that rings a bell. IPv6 also has that, but it's able to discover it more intelligently. So it's kind of just a graphic showing here that the IPv6, or ICMP rather, is an added-on header into those packets. So we'll look at some different stuff. But I want to talk about the MTU discovery that happens in IPv6. So the idea behind an MTU is we want to send the biggest packets that we can to prevent fragmentation of our data and the payloads that we're sending across the network. So our source node, this could be a host on the network, will send a packet out across the network that has the MTU size of its local link's MTU. So it connects to the router, figures out what your local router's MTU is, and sends out the packet with that MTU. And that's the biggest MTU that router's configured to handle. So this would be great if all of the routers from our host to our final destination use the same MTU. But the truth of the matter is, we cross links and we cross network segments that don't have quite the capacity that we do, and so therefore they might have a lower MTU packet. So if I cross a link that has a smaller MTU size, that link is going to send back a packet that says, hey, your packets that you're sending are too big. You need to scale that down. So my first packet makes it all the way across the network till it finds something with a smaller MTU. Then it gets sent back and says this is too big. So I retransmit the packet and I scale down my MTU. So I should make it through that smaller link and keep going towards my destination. If I reach another network with a smaller MTU yet, same thing happens. That gets sent all the way back to me and says you need to shrink this down a little bit. So the idea behind this is that by the time I get my first packet through from my source all the way to the final destination, I know exactly how big of a packet I can send to it. So if I know exactly how big of a packet I can send to it, we're just going to be sending whole packets across the network for that whole transmission, and we don't have to worry about fragmentation. Some of the problems we had with fragmentation were things like packets getting received out of order, packets getting lost and not reassembled correctly, and we had some problems with that kind of stuff. So it sounds a little bit inefficient at first when we're sending packets back saying this is too big, but the reality of it is a lot of that still happened in IPv4. This is a more efficient way of doing things. So we got just a few more kind of IPv6 big topics, and we'll get through pretty quick here. A couple things that we need to talk about. Neighbor discovery. So neighbor discovery is basically how our end devices find other IPv6 hosts on our network. And this is what you used to see with ARP. So IPv4 is just mapping a MAC address to an IP address. Same thing's really happening here, just it's called neighbor discovery, NDP. And we're doing this with multicast addresses. So when a host joins the network, it's going to send out some information, join that multicast group, and the whole network should know about where all of the hosts are, what their MAC addresses are, and those types of things. So the few packets that help us get through this, we're trying to figure out the MAC address of our neighbors. We still use those router solicitations and advertisements, so those are multicasts. But we also introduce neighbor solicitation, neighbor advertisements, and duplicate address detection, or DADs. So basically what we do here is we take an IPv6 that's designated by the 24 bits farthest to the right, so the remaining, very far 24 bits on the right, and that's added to the end of the multicast address. So I take FF02000001FF and then add on my 24 bits of my address, and that gets added into this multicast group. When a host looks up that address, the owner's going to say, here's the corresponding MAC address to that IP address. So high level, same thing as ARP, just handling it a little bit different way. So these neighbor solicitations, neighbor advertisements all happen with IGMP, and this is all done over multicast, so same kind of things like we saw before. Now here's something cool about NDP. If you think about IPv4, all of our hosts had one default gateway, and that's how we leave our subnet. If that default gateway goes down, that host can't leave its subnet. That's just a fundamental principle of how IPv4 works. In IPv6, we can do gateway discovery with NDP. So the idea behind this is that I can send out a multicast packet and try to get to the internet. So I'm saying, hey, I know what the internet is, I know my next hop, but how do I get there? So I send out those neighbor solicitations, or the router solicitations. I'm going to get back an advertisement from each of the routers that can get to that destination. So if my corp router goes down, I'll just send out a router solicitation. Corp2 is going to respond back and say, hey, I can get to that destination. Why don't you go through me? So it's really cool. It's kind of a self-healing thing that we can do with NDP. So I'll kind of skip through this here a little bit. Should be reading up a little bit on the NDP host solicitations and advertisements. But basically this is, at a high level, when a host comes online, auto-configures itself an address. It's just going to talk to those neighbors and say, does anybody else have this address? And it's going to try to avoid duplication. And that's what that DAD that we talked about before, duplicate address detection, was. So what this looks like is, my host created its address. It's going to send out an NDP neighbor solicitation and say, hey, I need all of your guys' MAC addresses. And the host will say, here's my MAC. So My host says I just made up this IPv6 address. Does anyone else have it? And of course, there shouldn't ever be duplicate MACs on a network, but just to be safe, we check. So the other host should say, no, that's not my address. Go ahead and use that. Last big thing we've got here before wrapping up is just talking about routing protocols. So it's probably a fairly safe assumption that all of the IPv4 protocols that we've learned about, RIP, OSPF, EIGRP, those types of things, still exist, but they've been tweaked. And any routing protocol that relied on broadcast traffic for obvious reasons is gone, right? So IPv6 doesn't do broadcasts. The protocols we're going to look at most, especially as we're starting out here, will just be static routes. You can actually do IPv6 RIP next generation, which we won't look at. EIGRP v6, basically the same thing, just a little bit of a different tweak for IPv6 support. And the other common one that we're actually going to look at is OSPF v3. So if you're looking for a CCNA exam objectives, make sure that you're studying at least the ones in bold here, static routes and OSPF v3. If you want that general, just net admin, kind of well-rounded approach to this, take a look at IPv6 RIP NG and EIGRP v6. So we'll go through some static routing here just to talk about this at a high level. Basically same things like we did before. You need a good network map. You need to know where your next hop is or what interface that you need to leave to get there. And you need to know what remote subnets that you have and what remote subnets that you actually want to allow your hosts to get to. And just remember, none of this matters if we use dynamic routing protocols. Those kind of take care of everything for us. So all we have to do, enable each of our interfaces for IPv6, configure all of our router interfaces with that address, make sure each of those routers can talk to each other, and we'll do our static routes just like we did with IPv4. And I'll put together a video on this as well. OSPF v3, same things. OSPF version 2 is IPv4, which is why we see OSPF version 3 is IPv6. It's a still link state routing protocol. We still have our autonomous system areas with a hierarchy. One difference is that OSPF version 2, we used a router ID, and that was determined by our highest IP address. In OSPF v3, we have to set that manually. So just a little bit of a difference there, but basically works out the same way. So we still use multicasts for any routing updates and acknowledgements, so nothing's really changed that way. So I think with that, I'm going to wrap this up here. I just wanted to give you, kind of an overview of what we read about a little bit, highlight some of the important things through that, get you some things to think about, and then set us up for some actual practical demonstrations and what we're going to be doing in our lab work as well.